Okay, hello everyone. Okay, this is a remake video for the introduction of the torsional indeterminate problem. Okay, the reason for me to remake this video because I want to fix some sign conventional issue in the previous video. Okay, so let's look at the topic of this video. Okay, this video is for the introduction for a statically indeterminate torsional load problem. Okay, this is just very similar to what we have learned in axial loading. Okay, in axial loading system, we also have the statically indeterminate problem. Okay, the concept for the statically indeterminate problem is that after you use the rigid body equilibrium, uh, you found you don't have enough equations to solve the unknowns. Okay, that's called statically indeterminate. And at this situation, you need to find more equation to solve the problem. Okay, and the additional equation, most of the time, these additional equations are constraint of the system. Okay, so let's look at this very typical torsional indeterminate problem. Okay, here is a bar. Okay, and it's fixed in the two walls. Okay, fixed in the two walls. Okay, and I apply a torque here, 500 Newton times meter. I apply a torque here, and then my question is find out the reaction torque at the A and B. Okay, what's the TA and TB? Okay, so because the whole system is is statics. It is static. The whole system is static. So rigid body equilibrium. So the resultant force and the resultant moment for the system is zero. And in this problem, because we only have considered a torque, okay, we don't have to consider force because in this system we only apply a torque. Okay, so we only have to consider the torque balance. Okay, because the rigid body equilibrium, so summation torque is equal to zero. Okay, and in this system, I just say we have applied torque here. Okay, and we have a reaction at torque at the A and B. So for TA and TB, okay, which direction I should assume for torque A and torque B? Or should I assume it's rotated in this direction or it's rotated in this direction? Okay, this one. Okay, which direction I should assume? Okay, the TA and TB, which direction I should assume? Actually, you can pick any rotation you want. Okay, so pick any rotation direction you want. Okay, but you have to define which direction is positive. Okay, so let me explain this in detail. So the reaction torque at A and B, torque TA and TB, which direction I should assume? Okay, you can assume anything you want. Okay, for this problem, okay, let's assume TA is rotated this way and TB is rotated this way. Okay, let's do this assumption. We assume TA and TB and rotate in this direction. And then I have defined, okay, let's make a definition here. Okay, I make a definition that, okay, this direction is positive. Okay, like this 500 here, this direction is positive. Okay, I assume this direction is positive. Okay, we assume this direction is positive. Okay, so what's the sign of the TA? If this rotated direction is positive, what's the sign of the TA? So the sine of TA will be minus, right? Okay, and plus 500. Okay, if I assume this direction is positive, what's the sine of the TP? Okay, okay, because this direction is positive, so that's why this direction is negative. So it's negative TB, and the total torque is equal to 0. Then we will reach a conclusion equation TA plus TB equal to 500. Okay. Okay, this is a rigid body equilibrium. Okay, after rigid body equilibrium, we only have this one equation, but this one equation will have two unknowns. So this equation is not enough for us to solve the TA and TB. So we need to find another equation. Like I say, for a statically indeterminate problem, we need to find the constraint of the system. So what's the constraint of the system? Okay, so so let's look at this free body diagram. Okay, so this problem. We can use the cut section method. Okay, let's make a cut section. I make a section here. I make a section here. Okay, so this is A C B, right? This is A C B. Okay, in this section, in this cut section, we have this. In this section, we have a torque AC, and in this section, we have a torque CB. Okay, so the torque AC in the AC section will cause a deformation, right? Okay, and the torque in TCB, for the torque at the CB section, TCB, it will also cause the deformation, right? Okay, let me write down this. Okay, so we have a TAC. It's also caused the deformation. Okay, AC. Okay, we also have the TCB. It also causes the deformations. Angle of twist, theta CB. Okay. Okay, so because this is we have to use this to find the constraint of the system. Okay, the constraint of system is this. Okay, let me write a conclusion. Let me write a conclusion. CB equal to 0. Okay, what does that mean? That means the deformation or angle of twist. Okay. Okay, that means angle of twist or the twist angle of twist must be equal and opposite in the AC section, AC and CB sections. Okay, this is a constraint of the system. Okay, why and why? Okay, this is actually it's very easy to find. Okay, we have deformation here, and we'll have a deformation here. Okay, angle of twist here and here, and why why it has to be equal and opposite? Because we use another way to prove this. If phi AC equal to phi CB, if phi AC equal to phi CB, okay, but that doesn't mean that means it's not a twist. It's not twist. It will become a rolling. Okay, yeah. Think about that. We have a shape, a bar fixed in the wall, and I make a twist. I make a torque inside. I make a torque on the shaft. Okay, a torque on the shaft. Okay, and okay, because it's a twist. Okay, it's a twist. So the angle in these two sections must be equal and opposite. That's called twist. Okay, I'm not sure you can think it's a twist. It's a twist. This way or this way. Okay, this way or this way. So the angle of my hand, angle of one must be equal and opposite. equal and opposite. Okay, that's called twist. Okay, if the same direction or the same amount, that means rolling. This is rolling. Okay, the same direction. This is rolling. Okay, right now we at the state of twist, twist. Okay, twist. Okay, this way or this way. Yeah, this way or this way. This is called twist. It's called twist. Right? Yeah, twist. Yeah, this is called twist. Equal and opposite. Equal and opposite. Okay, so that's the constraint of the system. Okay, the deformation at AC section and deformation of CB section must be equal and opposite. That means phi AC plus theta AC and theta CB, add them together is 0. Okay. So what's the formula for the angle of twist? Okay, don't forget the angle of twist is a TL over GJ. Okay, GJ. Okay, right? Okay. So we use this equation. So this with this is equation. That will become okay. TAC is TAC times LAC divided by GL plus TCB LCB divided by GL. Add them together equal to 0, and we assume the same material. Sorry, it's GJ. Sorry, GJ. We assume it's the same material, so the GJ is the same. The GJ for AC section and CP section are the same. So we can just times GJ in the both side of the equation, so we can ignore it. So what's the LAC and LCB? LAC is 3, LCB is 2, so we will have the equation like this: 3 TAC plus 2 TCB equal to 0. Okay, so we find another equation. Okay, so and don't forget we have the equation from the rigid body equilibrium. Okay, so we have TA and TB. Okay, here, sorry, I forgot the one thing. Okay, in this problem, I also need to use cut section method to get the TAC. What is TAC and TCB? Okay, so let me write it. We also need a cut section. Okay, cut section. I don't have space here. Where should I? I don't have space here. Okay, so where can I find more space? And do I have? Okay. Maybe let me open another panel. Okay, let me open another panel. Never mind. Okay, where should I? Whether should I? Okay. So I just erased everything here. Okay, if you want to know information, please rewind. Okay. Okay, let's use cut section method to obtain the TAC and TCB. Okay, so the cut section maybe we just draw from here. Here is A. Okay, and cut section here is the TA. We assume TA is this direction. There's another section here. This A. Cut section here is A. And then here is 500. And this is TA. And also at this cut section, we will have TAC. So what direction should I assume for TAC? Just don't forget, we also use the sign convention for the torsional load. Okay, right hand rule. We assume TAC is this direction. In this way, this use the right hand rule. The thumb direction is outward to the surface. Right hand rule, the TAC rotate in this direction. Your thumb direction is outward to the surface. Okay, so at this section we will have the TCB. Okay, in TCB you also assume is rotating in this direction, and the right hand rule tell you your thumb direction is point outward to the surface. Okay. Okay, and each section also we use a rigid body equilibrium again. We use a rigid body equilibrium again. Okay, so let's do the rigid body equilibrium as these two sections. Okay, okay, for the section one, okay, we have TA here. Okay, TA is rotate in this direction, or where is the thumb direction? If you rotate this direction, okay, use right hand rule. Okay, that means your thumb direction is in this way. Okay, thumb direction is this way. The thumb direction is in this way. That means what's the sign of TA? Because right now our surface is here, internal surface is here, and this is the thumb direction for a TA. So it's inward to the surface. So that means the minus TA. Okay, this means minus TA. Okay, on the TAC we assume positive. Okay, so it's equal to 0. Okay. Okay, now, okay, here we have the sorry, this I should make it up. It should be TA. It should be TA. Okay, we already know this direction. The thumb direction is here. So our surface here, so it's inward to the surface. So the sign of TA here is minus. And what's the sign for the 500? Okay, the 500 is rotate in this direction. Okay, use the right hand rule. Okay, here is the thumb direction, and the thumb direction is here. It's point outward to the surface. So the 500, the sign is positive, and then plus TCB. Okay, is equal to 0. So for this two rigid body equilibrium, it tells you that TAC is equal to. Okay, maybe let me write right here. So this just tell you TAC is equal to TA. So it's 3 TA. And the TCB, what is TCB? TCB is equal to 500. TCB is equal to TA minus 500. Okay, TCB is equal to TA minus 500. Okay, so equal to 0. Okay, from this equation you can so you will see this one. What's the final equation? 3TA plus 2TA equal to 1000. Okay, so the TA is 2000, right? Okay, TA is in 2000. Okay, we will solve the TA, right? Amazing, right? Amazing. Just use the constraint equation and the cut section method. We resolve the TA. Okay, and don't forget TA plus TB is equal to 500. So that means TB is 300, and its unit is Newton times per meter. Okay, and because we because our value is all positive, that means the TA, is really this direction. Okay, TA is really this rotation direction, TA. Okay, because our initial assumption TA is rotating in this way. Okay, and the value is positive. That means TA really rotates in this way. Okay, also TB, what's the rotation, the real direction for a TB? Okay, because initially we assume TB is rotating in this way, and we get a positive value. That means it really rotates in this direction. Okay, so you see for this problem at the very beginning, I say you can assume any direction you want. Okay, sorry, you can try yourself. If you initially assume if you initially assume TB rotating in this way, if you assume TB rotating this way, you will also get the same answer. Okay, you will also get the same answer here. Okay, you also get the same answer here. Okay, so that's why at the beginning I say for the torque at this reaction, you can assume any direction you want. Okay, but you have to define which way is positive and for the rigid body equilibrium. And then during the cross-section method, you need to also follow sign convention rule. Okay, in the cross-section method, in the cross-section analysis, you must have to follow the sign convention rule. Okay, so this is a basic introduction for torsional load statically indeterminate problem. Okay, so I will show another example for the torsional statically indeterminate problem later. Okay, see you in other video. Bye bye. Bye.